We are going to explore chemical reactions and the energy change that's usually involved with these reactions in this video. By the end, we'll look at specific heat problems. So a chemical reaction is anytime you have one or more substances becoming one or more new substances. Basically, it's a chemical change. We know that with a chemical change, you have a new substance or substances forming. It's the same thing as a chemical reaction. All right, they literally mean the same thing. So a couple vocab terms here. We look at reactions more later on in the course, but there's some basic stuff we can talk about. Reactants here are the starting materials in your chemical reaction, and products are what you end with. So your reactants become the products. So some examples here. I'm not even using the proper symbols and stuff yet. That'll come later. But just to give you an idea, if you took iron and sulfur and reacted them together under the right conditions, you would get iron sulfide. This is a chemical reaction, a chemical change. You got iron and sulfur, your reactants, your starting materials, becoming iron sulfide, your product. Okay? Some people may say, well, iron sulfide sounds a lot like iron and sulfur. Aren't they the same? No, they would have totally different properties. All right, and that's key. It's a totally new substance. So iron sulfide here would be like fool's gold. If you took sodium and chlorine and reacted them together, they would be your reactants. You would form sodium chloride. Think about this. Sodium is a metal that reacts violently with water. Chlorine is a toxic gas, but when they react and you form sodium chloride, it forms salt, something that you need to live. So you get a new substance here with totally different properties. That's a chemical reaction, a chemical change. So some examples here of chemical reactions. Photosynthesis is a great example. You can see here from this picture, the sunlight, the carbon dioxide, and the water go in, and your new substances, your oxygen and your glucose, come out. You got your new substances forming. That's a chemical change, a chemical reaction. Rusting iron, okay, becomes iron oxide. That's a chemical reaction. Anytime you eat anything, that's a chemical reaction. You're breaking down the molecules in the food, rearranging them, forming new molecules, giving off energy. This is a chemical reaction. There's a very good chemical reaction involving gummy bear, or sometimes you use other candy. I like to use M&M, and hopefully we see that in class. But it's definitely a good example of a chemical reaction. So anytime you have a new substance or new substances forming, that's a chemical reaction. I want to talk about the different chemical reaction indicators real quick. These are things that could clue you in that a chemical reaction has taken place. They don't always mean that a chemical reaction took place. You still need to get that new substance, but sometimes if you're on the fence here, they could clue you in that, oh, maybe a chemical reaction took place. So anytime you have an energy transfer, that could indicate that a chemical reaction took place. Something becomes hot or cold. So you use natural gas here, it burns, it's giving off heat to cook your food. That's a good example there of a chemical reaction. Color change is sometimes an indicator here of a chemical reaction. So, you take a bite out of your apple and leave it sit, it starts to turn brown. So the change in color tells you, oh, that's probably a chemical reaction. Or you burn your food. Good example there of a color change chemical reaction. Remember, you do need that new substance forming. If you were to paint a wall, that's not a chemical reaction because you didn't get a new substance. So again, you got to get the new substance, but these can sometimes help you figure out if a chemical reaction took place. Some other indicators here of chemical reactions, if you have a gas being produced, so bubbles forming, that could be a good indicator. If there was no gas present, now all of a sudden the bubbles are forming, that could tell you a chemical reaction took place. Like if you spray bathroom cleaner on a tub and it starts reacting and foaming up. Another example, something you might not be as familiar with, it's called a precipitate. Basically, in chemistry, we can mix two liquids and we get a solid that will start to form and settle out. I like to call it chunkage. It's like you mix two liquids and all of a sudden you get this like chunky material starting to form. A good example of this in the real world would be like cheese production. You mix the liquids and then you get the curds forming. This picture is showing you how we mix two liquids in chemistry class, and you can see this like solid chunkage that's starting to form. That's a precipitate. It's not, the precipitation that would fall from the sky. So we'll do a lot of precipitation reactions in chemistry. Basically, you get a solid forming. There's other indicators here, maybe sound, odor change, light. So as long as you got a new substance, then you can say that a chemical reaction took place. All right, these are just things to key you in that maybe one took place, but you got to get a new substance in order for it to be a chemical reaction. I'm going to quickly go through the three different reaction laws here that you need to know about. So we will talk about these or come back to these as we work through the course. So the law of conservation of energy basically says energy can neither be created nor destroyed. You can only change it from one form to another. So for example, you might eat food and say, well, food gives me energy. But you got to remember here, like if you're eating a carrot, all right, and that's giving you your energy, well, that carrot got the energy from somewhere. It got it from the sunlight. So all you're doing is really converting the energy from light energy to chemical energy. Or you eat that food, all right, the chemical energy that's stored in the food, and you turn it into mechanical energy to breathe or to ride your bike. All right. Same thing. You plug something into a wall. You're taking the energy here, the electricity energy, and you're turning it into something that's heating up your house or something like that. So the key is you can't create or destroy energy according to the law of conservation of energy. You can just transform it here. And we'll talk more about that. The law of conservation of mass is basically the same thing, but with mass. Mass can neither be created nor destroyed. So the total mass in the universe is constant here. So the easiest example I can give you with this is if you took 3 grams of a substance, reacted it with 4 grams of a substance, all right, how much product should you get? Well, you should get 7 grams. That would be the law of conservation of mass. All right. Your total amount of reactants should add up to your total amount of products. So definitely know these laws and know some examples. The third reaction law here is kind of a combination of the two, but it is a little different. So the law of conservation of mass energy basically says the total amount of mass and energy in the universe is constant. The easiest example I'm going to give you with this would be E equals mc squared, Einstein's theory. You don't need to be able to explain it or anything like that. Just know that this is an example of the law of conservation of mass energy, which says the total amount of mass and energy in the universe is constant. So know all three laws and at least know one example for all three. So now we're going to talk more specifically here about energy because energy is usually involved here in chemical reactions. So the formal definition of energy is the ability to produce change or do work. So we have another unit coming in here. The SI unit for energy is the joule. We use capital J for that. Another unit you might see here is like the calorie. So there are some more conversions you need to know. You got to add these to your arsenal here of your conversions. You're responsible for knowing these. 1 calorie is equal to 4.184 joules. Okay, this is not the same as the calories in food. Okay, that's usually like a capital C calorie. This is different, but 1 calorie equals 4.184 joules. And then you can apply this to, other prefixes here that you might see with conversions, like 1 kilocalorie is equal to 1,000 calories, or you could say, there's 1 kilojoule for every 1,000 joules, right? So definitely be familiar with these new units and the conversions. So as I said, we're going to talk about energy here. So thermodynamics is just the study of energy and how it can be kind of converted here or transformed. So anytime you hear the word thermodynamics, don't get scared. It just literally means we're talking about energy. So we said that, energy can neither be created nor destroyed, but you can transform it. So, potential energy stored in the bonds of a substance can, break and turn into the energy we need to move. So potential energy can become kinetic energy or the energy of motion. But what happens in these reactions is that usually there's some form of heat or energy transfer that's taking place. Almost every reaction is either taking in heat or giving off heat. So just so you're aware, if you ever see these terms, the system is the part of the universe that you're studying, so it's what you're looking at, and the surroundings would be outside of that. So if you ever hear about, heat coming from the surrounding, it basically means it's coming from outside the part that you're looking at or the system. So definitely here understand that thermodynamics, we're talking about energy and how we're transforming it and looking at the heat involved. Two terms you need to be familiar with here for this heat transfer is exothermic and endothermic. If you use the words to help you, you will never forget these. Exothermic is when energy is released in a reaction. So EX for exo, EX for exits. Okay, the energy is exiting. So you feel it being given off. So something would feel warm. So if you're burning something or something's giving off heat, you're going to feel that heat. So it's an exothermic reaction. The heat is exiting. An endothermic is reversed. Energy is absorbed or it's entering. En for endo, En for enters. All right. So if the energy is entering the system, it feels cold. All right. So if you were to break open one of those portable instant cold packs, it would feel cold because energy is entering the system. Therefore, you feel the cold because the heat is essentially leaving. So definitely know the difference between endo and exothermic. This brings us to something called heat capacity. Heat capacity is how much heat is needed to increase the temperature of an object by 1 degree Celsius. So if you wanted to bring the temperature of a substance up by 1 degree Celsius, how much heat would you need? But you need to realize here, this would be an extensive property. In an extensive property, the amount matters. So if you had a little ice cube versus an entire iceberg, the heat capacity is going to be different, even though they're both ice, okay? Because you have a different amount of each. It's going to take a lot less energy to bring the ice cube up by 1 degree Celsius than bring up the entire iceberg by 1 degree Celsius. So you couldn't really compare substances here. So we created something basically that's a little bit more specific. It's called specific heat capacity. And you use the letter C or CP to stand for specific heat. And basically, this is the amount of heat needed to raise 1 gram of a substance by 1 degree Celsius. So now you can compare substances because you're talking about the same amount for every substance here. So, for example, water has a relatively high specific heat. It's 4.184 joules per gram degree Celsius. You do need to know the specific heat of water. Just like you needed to know the density of water, you do need to know the specific heat of water is 4.184 joules per gram degree Celsius. And that's just the units here we use for specific heat. Basically, what that means is since water has a high specific heat, it takes a lot more heat to raise the temperature of the water. And you might say, well, 4.184, that doesn't seem like a high number. Well, if you compare it to metals, metals usually have specific heats that are in the decimals, so it's definitely higher. So metals have a low specific heat, takes much less heat to raise their temperature. Easiest way to think about this is if you had the exact same amount of a metal and water in the parking lot on a hot summer day, and you left them there for a few hours and you had to go up and touch one, which one would you want to touch? The water, okay? Because for the water, even though they're both sitting out in the sun, the water is going to be cooler because it takes more energy to raise the temperature. The metal is going to be much hotter because it takes less energy to raise the temperature up. So if you had a string of, 100-degree days and you go out to your pool's probably not going to be 100 degrees because it takes a lot of energy to bring the temperature up. And that's why, the ocean life typically love that because you get a hot day, the water doesn't automatically go up to a super hot temperature. It takes a lot of energy to bring the temperature of the water up because the water has a high specific heat. So another example here of this idea of specific heat, if you put a wooden spoon and a metal spoon in a pot that's cooking on the stove, and you went up to the spoons, the metal spoon would be too hot to touch after a while because it has a very low specific heat, whereas the wooden spoon has a higher specific heat, so you could go up and grab it and you don't feel the heat in that spoon. And this is also why you use metal for your pots and your pans because they have a lower specific heat, they heat up faster, and they cook your food better with less energy. Now we're ready to do some specific heat problems here. We already said the units for specific heat are typically going to be joules per gram degree Celsius. It's some form of energy unit per mass unit times a temperature unit. So maybe you could see this in like calories per gram degree Celsius, all right? But get used to seeing that joules per gram degree Celsius, that's the units for specific heat. So the equation we use for this is Q equals mc delta T, All right. Sometimes kids like to call this Q equals MCAT. All right. So you need to know the equation, that's first, but you also need to know what each of the letters means and what the units should be for each. That's very important here. All right. You can't do these problems if you don't know the equation and you don't know what the letters mean and what the units should be. So Q is going to stand for the heat or the energy here, and it's going to be in joules. Q is not temperature, it's heat. It's typically going to be in joules or something like calories. All right. M is mass, and that's going to typically be in grams. C, we already said, is specific heat. It's going to be typically joules per gram degrees Celsius. The units of your specific heat are basically what's driving the other units in the equation. And delta T stands for the change in temperature. It's not just T, it's not just the temperature, it's the change in temperature. So it's always the final minus the initial temperature, and it's typically going to be in degrees Celsius. So you got to watch these units here. Make sure your units are right when you're setting up these problems, but you need to know what each of the letters mean. So Q equals MC delta T. You definitely need to know this equation and be able to use it in problems. Let's jump right in and try one of these problems. So for this example, it says when 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85 degrees Celsius. What is the specific heat of the olive oil? All right, so we immediately know we have to use our Q equals MC delta T equation. All right. And you have to figure out what letter am I solving for. Typically for these problems, you're going to be solving for one of the letters, and that means you know everything else in the problem here. So the question is asking us to find the specific heat of the olive oil. So remember, specific heat is C. So you need to know what these letters mean so you can figure out your problems here. All right, that must mean you know everything else in this problem if you're solving for C. So let's start plugging in. Q. All right, in your head, you should be saying, okay, what is Q? Oh, Q is heat. Typically, it's going to be in joules. Well, they gave you 435 joules. So you know the value of Q, right? M is going to be the mass. They told you had 3.4 grams here. C is what we're solving for, so we're going to leave that as our variable. And delta T is the final minus initial temp. So you got to be careful here. You're typically going to have two temperatures. You might have to sift through the problem. The higher number does not automatically make it the final temperature, so be careful. But this problem does say the temperature increases to 85. So that's what we're increasing to and ending with. So 85 is our final minus our initial. They told us it was at 21 degrees Celsius. So delta T is final minus initial. All right, so we plugged everything in. Now we're just ready to do math here to solve for C. All right, so I'll show you how to do this, and then I expect that you'll be able to do this math every time. So the first thing I would do to solve for this one is I would do my subtracting here, the 85 minus 21, and I'd get 64 degrees Celsius, okay? So now what you're going to do here is I would multiply the 64 times the 3.4. So you can drop off your units here as long as you pay attention to your final answer, having the units, what units it should be, all right? Make sure you're plugging in the correct units here for the problem. Mass is typically grams, specific heat is typically joules, temperature is typically degrees Celsius, and so on. So when you take the 64 times the 3.4, I have the 435 equal to now the 217.6 times C. So all I did was subtract the 85 minus 21 first, got 64, 64 times 3.4, and now I have 217.6 times C remaining on the right, equal to the 435 on the left. So I have to solve for C. So you divide both sides now by the 217.6, and then you will now be able to solve for C here. So you do need to watch sig figs, all right? Typically here, we're doing a lot of multiplying, dividing, so go back to your original problem, count sig figs and use the least. So it looks like in this problem, the lowest amount of sig figs we have are 2. So your answer has to have 2 sig figs. So when you round this correctly and you do the math, it should come out to be 2.0 with 2 sig figs. I think it comes out to be like 1.99 something. So 2 sig figs is 2.0. And be careful with your units. You were solving for C, which is specific heat, and you need to know that specific heat has joules per gram degrees Celsius. All right, and those units do check out here in this problem. All right, this is not something you can just guess on. You have to know this. The units for C are joules per gram degree Celsius. So that has correct sig figs. It has units. I, circled my final answer and I showed all my work. This is the minimum amount of work you would need to show here to get full credit on one of these problems. So know what the letters mean, know what the units should be, then you just plug in and solve and watch your units and sig figs. So let's try another example here. This problem says how many calories does 32 grams of water absorb when it's heated from 25 degrees Celsius to 80 degrees Celsius. So I know it's going to be a Q equals MC delta T problem. They're asking how many calories. So in your head, you're going to say, okay, which of these letters would give me calories? Well, calories is a form of heat, so it's going to be Q. Remember, typically here in these problems, this is where knowing your units is important. Q is going to spit out joules. Well, they want calories. So that means you're probably going to have to make a note to yourself here and say, oh, I'm probably going to have to convert at the end of this problem. So be careful. You do got to watch your units here with these problems. All right. Q is going to typically spit out joules, not calories. That's something you'll have to watch for. So that means I'm solving for Q. So that means I should know everything else in the problem. I'm just going to start plugging in and solving. So for the mass they gave me was 32 grams. Do I like grams for mass units? Yes, that's what I want. So I don't have to worry about converting that. All right. C here, specific heat. In your head, you should be saying, okay, well, typically that's joules per gram degree Celsius. You might say, well, oh, I don't see a specific heat in this problem. I know that I'm solving for Q, but I don't see the specific heat here. Anytime you have a problem like that, where you're like, I know I'm solving for like a different letter, but I don't see, specific heat anywhere in the problem, pay attention to the substance. We're using water in this problem. Anytime you have water, you are supposed to realize that you know the specific heat of water. All right. Remember, the specific heat of water is 4.184 joules per gram degrees Celsius. So just watch for that. If you're using water, you are supposed to remember that you need to know the specific heat of water. 4.184 joules per gram degrees Celsius. And then delta T is the final temp minus the initial. So it looks like we're going from 25, which was our initial, to 80, which was our final. So 80 minus 25 degrees Celsius here. So this one, the math is a little bit easier to solve. Again, I would do my subtracting first, and you get your 55 degrees Celsius. And then I would just take 55 times 4.184 times 32. When you do that, you should get 7363.84. And remember, your units for Q, this is where you need to know your units. Your units for Q here should be joules. All right, if you pay attention to your units up there in the problem, the grams would cancel out, the degrees Celsius would cancel out, you'd be left with joules. So yes, the problem wants calories, but your Q is in joules. So you're going to have to convert here. So multiplication symbol, conversion line. I know that joules need to go on the bottom for them to cancel. The conversion here is that there's 4.184 joules for every 1 calorie. Joules on top and bottom, they cancel. Now you're in calories. You do need to watch your sig figs. So go back to your problem, count sig figs, use the least. It's going to be 3. So your answer for this should be 1760 calories. All right, that's correct. Units and sig figs. All right, so this is just showing you another different example here for Q equals MC delta T, specific heat problems. And remember, you do need to know the specific heat of water. There's another form of specific heat problem that I want to show you, and these problems use the idea of calorimetry. So calorimetry is just a fancy word for saying we're going to look at the science of measuring heat. We're going to look at the temperature changes and figure out the amount of heat that was transferred. So the device we use for calorimetry is a calorimeter. Basically, the easiest calorimeter we would use is a foam cup. Foam cups are really good insulators. So, even in college, we use foam cups for this. You just basically take one cup, put it in another, and you do your reaction inside the inner cup. And, it's really good at kind of holding the heat. So if you ever see the term enthalpy, which we denote with the letter H, it's just another word for energy. Just like thermodynamics is, talking about energy, enthalpy is just another way for saying, hey, we're looking at the energy flow here as heat. So these calorimetry problems are going to use this big idea here. It's shown here, it's plus Q equals minus Q. So you have to take this idea into these calorimetry problems and realize essentially what you're doing is two specific heat problems in one. All right, so plus Q equals minus Q. What this is saying is this, and it's pretty easy to understand. It looks scary, but it's actually pretty easy to understand. What this is saying that is that the heat that is lost by one substance has to be equal to the heat gained by the other. Okay, so think about this logically. If you were to take a piece of hot metal and put it in water, what would happen to the temperature of the metal? It should go down, right? Essentially, the metal would be losing energy here, right? But where is that energy going? Oh, it's going to the water, all right? So the water would get warmer. Water just can't get magically warmer. Remember the law of conservation of energy? How did the water get warmer? Oh, it came from the metal, right? The key here, what this is saying is, though, that the amount of heat that is lost by that hot metal is equal to the exact same amount that the water gained. The only difference here is the sign. If the metal lost a specific amount of heat, according to the law of conservation of energy, the water had to gain that exact amount of heat, but it's gaining it, so it's a positive. Okay, so the reason why the water got warmer is because the metal lost the energy. So we're going to use this idea of plus Q minus Q in problems here. Essentially, like I said, it's just two specific heat problems in one. So now we're going to try another problem here. All right, if you notice, there's a lot more going on here, but I'm going to point out how you know this problem is different. So first, we have an unknown metal with a mass of 75.8 grams heated to a temperature of 80 degrees Celsius. It's placed in 79.4 grams of water that is at a temperature of 18.5 degrees Celsius. The temperature of the water and the metal then rise to 23.5 degrees Celsius, and we want to know the specific heat of the metal. All right, so the key is, how do you know if a problem is a simple Q equals MC delta T, where you just plug in and solve for one of the unknowns, or if it's one of these plus Q minus Q problems? So you have to be able to look at a problem and know, hey, look, it's just a simple Q equals MC delta T, or it's going to be a little bit more fun, plus Q equals minus Q1. The key here is, if you're just talking about one substance, it's going to be a Q equals MC delta T problem. If you notice all the other examples we did, the one was using just olive oil. It was talking about just olive oil. That was a Q equals MC delta T problem. The other example we did was just talking about water. One substance, Q equals MC delta T problem. All right, as soon as you start mixing substances or taking a substance and putting it in water, boom, you know that's a dead giveaway. It's going to be a plus Q equals minus Q problem. All right, so you do have to be able to pick that out in the problem. I can see in this problem that I have a metal being heated and placed in water. That's a dead giveaway that immediately I know it's going to be a plus Q equals minus Q problem. These problems do take up space, so I'm going to try to fit this all in here. But you need to write that. The plus Q equals minus Q must be written, because that's going to allow you to do the sign switcheroo in the problem. All right, and I like to label this. I like to say, okay, in this problem, who's going to be the minus Q and who's going to be the positive Q? So in this problem, who is losing the heat? Well, think about it. If you're taking the hot metal, you're putting it in water, the metal's going to get cooler. So the metal is going to be losing the heat, and then the water is going to be gaining that heat. So any heat that is lost by the metal is going to be equal to the exact same amount of heat that is gained by the water here. That's why it's a plus Q. All right, so you must have the plus Q equals minus Q written, or you lose points. All right, so now it's important to say, okay, what are we solving for in this problem? So this problem says, what is the specific heat of the metal? All right, so that means in this problem, we are going to need to end on the metal side. All right, as long as we're not solving for the final temperature, you can kind of split this up into two separate problems, and it kind of makes your life a little bit easier. So I know that I'm trying to find the specific heat of the metal, so that means I want to end on the metal side, so that means you start on the other side. So I'm going to start on the water side here. All right, so you would say, okay, well, what's the Q of water? Well, remember here, you do know what Q equals. Q always equals mc delta T. So you're going to start with Q equals mc delta T, but we're specifically starting on the water side. So all these numbers are going to relate to the water only. That's very important. There's a lot of numbers in these problems. You got to watch your units and you got to pay attention to what you're doing. You really need to think through these problems. So I'm going to end on the metal side. So that means I'm starting on the Q of the water side. And we already know that Q equals mc delta T. All right. So there should be just one thing that you don't know here in the problem for Q equals mc delta T for the water. So if I look at the problem, Q I know is joules. Do I see anything relating to joules here for the water? No. So that means I must be solving for that for the water. I don't know the Q of the water. So that must mean I know everything else about the water. So the mass of the water. If you look at the problem here, they told me the mass of the water is 79.4 grams. All right, we want it to be in grams, so that's good. C. C is specific heat. That's typically joules per gram degree Celsius. I don't see that anywhere in the problem. But remember, this is water. So you need to know that it's 4.184 joules per gram degree Celsius for water. You need to know the specific heat of water. And then delta T is final minus initial. So it says that the final temperature of the water and the metal is 23.5. All right. Realize here, because the water and the metal are sitting together, you took the metal and put it in water, they always end up at the same final temperature. So they may not specifically say that the final temperature is for the water, but realize if you know the final temperature of the metal, you know the final temperature of the water. All right, minus the initial. Remember, delta T is final minus initial, and the initial temp of the water was 18.5. All right, so when you do your math here, do your subtracting first, multiply it by 4.184 times the 79.4. The Q of the water comes out to be, remember, don't sig fig this yet, don't round this yet. It comes out to be here 1661.048, and your units for Q are joules. All right, so what this is saying is that when you take this hot metal and put it in water, the water is gaining 1661.048 joules, right? But where did that come from? Water can't just magically gain energy. The law of conservation of energy says that can't happen. So because we wrote this plus Q equals minus Q, if the water gained that much energy, that much heat, it had to come from the metal losing it. So now you know the Q of the metal is equal to the negative of that number. Okay, because you wrote the plus Q equals minus Q, you can do the sign switch here. All right, all you did was take that exact value and put a negative in front of it. So the amount of heat that is lost by the metal is equal to the amount of heat that was gained by the water. The only difference is the sign here. So now we know something about the metal side. So now we're ready to move up. All right, we're ready to take our problem and go up here and deal with the Q of the metal side. We said that's where we wanted to end. So you might say, okay, well, I don't know anything about the Q of the metal other than this value down here. Well, that's not true. You know Q for the metal is going to be equal to mc delta T, all right? So it's just a second Q equals mc delta T problem here. So plug in what you know and solve for your unknown. So for the Q of the metal, we just said, we found this here at the bottom. That's going to be negative 1661.048 joules. The mass of the metal, according to the problem. Now you got to be careful here. This is where your organization is important. You have to make sure you're realizing you're dealing with the metal side now. So you need to pick out the numbers relating to the metal. Well, it told me that there was 75.8 grams. Grams are the units I want. C for the metal, that's what I'm solving for. I'm solving for the specific heat of the metal. And then delta T of the metal, final minus initial. Remember, the metal and the water are at the same final temperature. So 23.5 is the final temperature of the metal minus the initial temperature of the metal. Be careful here. Make sure you're picking out the right temperature. And that was 80. Okay, so if you notice here, it's very important to point out, when you do your subtracting for your final minus initial for the metal, it comes out to be negative. Does that make sense? Well, yes, because the metal got colder. So it essentially lost temperature, not to mention the negative from your temperature change would cancel with the negative for your Q here, and that would give you a positive specific heat. It would cancel out. You can't have a negative specific heat. So now you just got to do your math and solve for C. All right, so we saw an example like this where you had to do the math to solve. So when you do solve for C with correct sig figs and units, it should come out to be 0.388 joules per gram degrees Celsius. So make sure you can actually plug that in and get that number. All right, and because it's specific heat, it's joules per gram degrees Celsius. So the easiest way to do these plus Q minus Q problems are to figure out which side you want to end with, start on the other side, and then do your sign change, and then finish the problem on the side that you need to end with here. So essentially, it's two Q equals MC delta T problems. Remember, you need to look at the problem and realize it's a plus Q minus Q problem because you are mixing two things, or you're talking about taking one substance and putting it in another. That's how you know it's one of these plus Q equals minus Q problems. If all you're doing is talking about one substance in your problem, then it's just a simple Q equals MC delta T. So you can set this up as two kind of separate problems as long as you're not solving for the final temperature. All right. Because the final temperature is the same on both sides, if you were solving for the final temperature, you would have to set this up as one massive equation and solve for your variable. Because you wouldn't know it on both sides, you would have too many variables. You would have to set this up as one massive equation. But as long as you're not solving for the final temperature, you kind of solve one side and then you go and get the answer you're looking for on the other side. So plus Q equals minus Q. Definitely a big idea. You need to be able to do these problems.